Hey folks, this last video in Lab 4, this last example in Lab 4 is a veritable potpourri of new R functions. We are getting into multiple mean comparisons, so as opposed to orthogonal contrasts that are planned, 1 degree of freedom tests that partition variance very cleanly, here we are looking at unplanned tests, and we're looking at a lot of pairwise comparisons, and we have a whole slew of potential tests that we could use, each of which approaches this question of error control in a slightly different way. None of these tests that we're going to be using are available in the base installation of R. We have to reach out and bring in some new packages. In particular, we are going to bring in the package Agricola. We have it mentioned here in the lab handout. We're going to bring in the package Agricola. That is going to bring with it a lot of test functions, LSD, Tukey or HSD, the Chaffee test, Duncan and SMK, so both fixed and multiple range tests. We will have to go into the multcomp package to get the Dunnett test. That's where you're comparing every treatment level to the control. And we have to reach out to yet another package called MUTOS to get the RAGWQ test, and you will see that there's some slight complications in installing that, but we'll hit all of that. For the sake of demonstrating all of these, I have a cooked up data set for you, so let's bring that in. This is the Clover data that we talked about, I don't know, last week sometime, where we had different strains of inoculum, and we are inoculating clover. I'm going to refer to this as clover.dat. And bring this in. So if you remember this data set, we had different cultures of rhizobia, and we were measuring nitrogen fixation, or its ability to fix nitrogen with the clover plant. All right, let's go to it. It's a very simple CRD. Of course, you're going to check out the structure first. R interprets culture as a factor. Great. And we run the linear model where n level equals culture. Simple CRD, and look at the ANOVA. The ANOVA tells us that there's an effective culture, but that's not that informative. We want to know who's the winner, what's the best one, who's the loser. So really we want to look at ranking these various treatment levels and seeing where the significant differences lie. Let's start off with the easy ones. Let's go pick up the Agricola package. I've already installed it here. I've already installed it on my computer, so all I need to do is activate the package. So it's reaching in and activating library Agricola. If you haven't already installed it, you would go to install packages, type in Agricola, and install. Once you have it, you have a bunch of nice functions all available to you, and they are shown here in the script. If you want to run an LSD test, which is essentially a multiple t-tests. So here the alpha is simply the comparison-wise error rate, and the test itself has no idea and doesn't care how many such questions you're asking, and so therefore the experiment-wise error rate is not controlled. You simply call on it with lsd.test, and the arguments you feed it are the model itself, clover.mod, that is our linear model from up here, and you specify the treatment, the levels of which you want to make pairwise comparisons among. So in that case, it's culture. If you go back to the data set, that is the header for the column for the treatment levels that we're trying to compare. So it's just lsd.test, clover.mod culture, and I'm assigning it to an object because it's something funny with Agricola. If you just run this on its own, it doesn't show you anything at all. What you have to do is you have to assign it to an object. I'm calling that object LSD. And then you can take a look at that object. And what you will see are all the stats associated with it, the t-values that were used, but in the end, what you really wanted, this means comparisons table, where it lists the 6 treatments, has the means of each, and then gives you letters declaring whether or not 2 levels are significantly different from one another at your specified type 1 error rate. Now I should say Agricola assumes that your default type 1 error rate is 5%, but you can override that on any of them, for example, in Clover dot in the LSD, you can override on any one by essentially setting alpha equal to some other value. So I could put 0.1 here, run that, and run the LSD, and I'm going to get a different table here than I got here. Here, for example, you can see the letters have shifted somewhat, and that's due to a differently imposed type 1 error rate. But if you don't specify the alpha in the line, it's going to assume good old type 1 error rate of 5%. The syntax for the other tests are very similar. If you want to run a Tukey test, it's hsd.test instead of lsd.test, and if you want to run a Scheffé test, and remember Scheffé is protecting you, it's controlling the experiment-wise error against the whole range, not only of all possible pairwise tests, but all possible group comparisons as well. So it's a relatively insensitive test and conservative, but not likely to lead you to false positives. And in each case, I run the test, I give it a name. So here I could call in the Tukey object, it gives me my means comparison table. I could call in the Scheffé object, it gives me my means comparison table. Within Agricola, the multiple range tests have similar syntax. You can run a Duncan test or an SNK test, and I refer you back to the lecture notes and readings for characteristics around those two tests. What I do want to jump forward to, because it has some slightly different syntax, is the Dunnett test. And Dunnett test is something that is used quite often. This is a test where you would like to compare every treatment level to a control. And so you're not running all possible pairwise comparisons like you're doing with Tukey. You're actually running a smaller set of tests, and because there are fewer questions being asked, you can run those tests with slightly higher power than you can with Tukey, while still controlling the experiment-wise error rate. Unfortunately, Dunnett is not available within Agricola. It is available within this package MultComp. I have that on my computer already, somewhere down here. MultComp, and I have it already activated. If you need MultComp, you go shopping in CRAN and grab it and install it. Once MultComp is installed, you can access the Dunnett test with some fairly complicated looking syntax, but again, like with all these scripts, I'm giving you the template here so you don't need to go figure all this out. If you want to run a Dunnett test, use this line of code right here. You're running a general linear model. This GLHT is the function within the MultComp package that you're using. You apply it to the model of interest, Clover.mod. And this is a linear fitting algorithm, this LINFCT. Multiple comparisons is the MCP. And here, you declare the factor of interest. For us, that's culture. And we're doing multiple comparisons according to Dunnett. So when you run this particular line, the only things you would change are the name of the model, Clover.mod, and the name of the factor, culture. Everything else stays the same. You run that, and then you ask for the confidence intervals, and what you get is not exactly a table of differences among means, a mean separation table. What you get are 5 lines here where each line is comparing each treatment level to a control. And there's a couple things to note here. To interpret whether or not there is significant difference between 3DOK1 and the control, you have to look over here at the lower and upper bounds of the 95% confidence interval. In this particular case, that confidence interval does not contain 0. These are both positive values. And because they do not contain 0, we would reject the null hypothesis that the difference between these is 0. So I do have a significant difference between 3DOK1 and the control. On the other hand, if you look at this next line, my lower confidence boundary is negative, my upper boundary is positive. This 95% interval does contain 0. Therefore, I'm unable to reject the null hypothesis that the difference is 0. So whereas I would declare a difference between 3DOK1 and the control, I would not declare a difference between 3DOK13 and the control. The other thing that you have to note here is you've noticed I put a 1 in front of my control name. And I did this all the way back in the original data set. I changed COMP to 1 COMP. The reason I did that is because in the MultComp package, when you're running a Dunnit test, and I have this in the script here, the Dunnit test uses the first treatment alphanumerically as the control. So if you want, if you have a control that you want Dunnit to recognize, you need to make sure that it is the alphanumerically, that it is the first treatment level in all your treatment levels. And the easy way to do that is just to throw a 1 in front of it. You know, you could throw a bunch of A's in front of it or something, but you're basically tricking Dunnit into ranking that one first alphanumerically, because that's the one it's going to grab as the control. If you didn't do that, all of these linear hypotheses would be compared to a treatment level that you weren't particularly interested in. So that is the Dunnit test, and that's how you would interpret the output. The final test is also a multiple comparison test. This is the REGWQ test. This one is a little bit convoluted to access. You need the MuTOS package, and that would be fine. Unfortunately, MuTOS has a dependency called MultTest, which is no longer supported on CRAN or available on CRAN. So in order to get MultTest, you need to run these 2 lines of code. You're going to go to Bioconductor. It's another site, another archive of R packages and R code. If you run these 2 lines of code, it's going to reach out to the Bioconductor archive and grab MultTest. Once that happens, then you can install MuTOS as usual. And once you have it, running the REGWQ analysis is quite simple. It's just REGWQ, reference the model. For whatever reason, you also have to reference the data set here, and you have to specify an alpha. The unfortunate thing about this, when you run this, you get a lot of data. First of all, you get warning messages, which you can ignore at the bottom, but the kind of output you get is quite inconvenient. It's saying that you have 15 hypotheses that you're running. Down below here are those 15 hypotheses, and they are all pairwise comparisons, exactly as you would expect. But to decide whether or not any of these comparisons are significantly different from one another, you have to run back up here, and you could look at either this list of rejected null hypotheses. So comparison 1, for example, was rejected. What that means is that this first comparison of 1 versus 13, the null hypothesis was rejected, and so 1 and 13 are significantly different from one another, with a very high critical value, 15.66, and a very, very low p-value. And you would see this here, that p-value is close to 0. So you have to sort of parse through this output, pair by pair by pair, and decide which are different and which are not. In the end, if you do all of that work, and that's what I have here in the handout, let's see, yeah, here in the handout I sort of wade through all the output from all these tests, and here's the REGWQ. This is the output you get. If you wade through all this output, you can construct for yourself a mean separation table with the appropriate groupings. I encourage you to look at the second to last page of the handout. What I've done is I've grabbed the result of every single test and put them side by side, along with whether or not they control the error rate and what their least significant difference is, if it's a fixed test, or what the range of those differences are, these sort of protection levels are, if it's a multiple range test. And you can see, and I have some text here where you can squint at this a little bit, and you can see how the EER, those controlling error, are less prone to false positives than those that don't. So not very interesting, except it just shows you the syntax of how to run all these tests, and it's also worth looking at the box plot on the next page and looking at that in terms of, or in the context of, the results you're getting from these different tests. And that's about it. Okay, bye.